Hello mathematicians, we begin our look at the binomial theorem by looking at the Pascal triangle, or as it's more commonly called, Pascal's triangle. So Pascal's triangle can be built up as shown below, and there are a few points worth noticing about this particular pattern. The first one is that each row starts and ends with a 1, so we can observe that. The second is that each row is reversible, so whether we read left to right or right to left makes no difference. And there is symmetry as a result of that. Every number in the triangle, apart from the ones, is the sum of the numbers diagonally above. So as I'm sure you've seen before, if we take 1 plus 1, that gives us 2. And this 1 plus that 2 gives us 3. This 3 plus that 3 gives us 6, and so on. So this triangular pattern, where every number in the subsequent row is the sum of the two numbers diagonally above, is a fundamental of Pascal's triangle. The other thing which might not be so obvious at first glance is that the sum of each row is actually 2 to the n. So we have this 1 by itself up here. That's actually referred to as the 0th row, for reasons which will become apparent. The term with 2 rows in it is the first row, then we've got the second row, third row, fourth row, and so on. And the sum of the numbers in each row corresponds to 2 raised to the number of that row. So 2 to the 0 is 1, so there's one number. So there's 1 as the total of those numbers. 2 to the 1, because 1 plus 1 is 2. 2 to the 2, because 1 plus 2 plus 1 is 4, which is 2 squared, and so on. So again, just another peculiarity of Pascal's triangle. And there are, if you look up Pascal's triangle, you'll see that there are literally dozens of patterns within the triangle. But we'll be focusing on those which are most useful for the maths applications that we're looking at. So if we continue, the first application that we're going to work with is the expansion of a binomial. So we know that a binomial just means something with 2 terms in it. So I'm looking at a plus x, but there's absolutely nothing important about that. So it could be a plus b, it could be x plus y, it could be 1 plus x. So any combination of 2 terms. And we're going to consider the cases going from n equals 0 to n through to n equals whatever we like, where n is an integer. So if we then take what we know of Pascal's triangle and build in this expansion of the binomial into the pattern, we can see some more stuff emerge. So in our 0th row, we can think of that as a plus x raised to the 0 power. So anything to the 0 power, of course, is 1. And again, the sum of the coefficients is 1. Let's just jump down a couple of rows here. So in our 3rd row down, which is a plus x squared, then we've got this. So I went here because this is a pattern we're familiar with. So again, the sum of the coefficients, the 1 plus 2 plus 1, is 2 squared, because we're looking at a plus x all squared. And the way that the pattern evolves is that the first term in here, whatever it is, begins with the highest power. So it begins with the power outside the brackets, the value of n, and it drops down by 1 as we go across. So it goes a squared, a1, a0, which is of course 1, so we don't bother writing it. And the other term does the reverse. It goes up by 1, so beginning with 0. So we've got x to the 0 just here, which is 1, so we don't write it, x to the 1, and x squared. When we get down to something like a plus x to the 4th, where the sum of the coefficients is 2 to the 4th, and the values of the coefficients we can work out from Pascal's triangle, then we can see that the a goes down in power as we go left to right, from 4th to 3rd to 2nd to 1 to power of 0, and the x goes up from 0 to 1 to 2 to 3 to 4. So that's a generalized pattern for the expansion of any binomial. This little bit here is interesting, that we can actually see why the sum of the coefficients is 2 to the n, because if we let a be 1 and x be 1, then all of these bits end up working out to be 1. So what we're left with are the coefficients, the 1 plus 4 plus 6 plus 4 plus 1, which adds up to 16, of course. But over here, when we put the 1 there, we've got 1 plus 1, which is, of course, 2. So we're saying that 2 to the 4th equals 1 plus 4 plus 6 plus 4 plus 1. So it's a very elegant little proof as to why the sum of the coefficients across the nth row is actually 2 to the n. Now, the exercises, they can be tedious, but you just have to be careful. So use Pascal's triangle to write out these expansions. Now, for the moment, we're going to operate with Pascal's triangle as built up previously. But after a little while, we're going to see that we can generate Pascal's triangle, in a sense, with our calculator. But for the moment, if we look at 1 minus x to the 4th, then when we expand that, the coefficients we know will be, from the triangle, 1, 4, 6, 4, and 1. And this first term here goes down in power, so we've got 1 to the 4th, 1 cubed, 1 squared, 1 to the 1, and 1 to the 0, which is 1, and we don't bother writing it. And this term, including the sign that goes with it, is going to go up. So we've got minus x to the 0, minus x to the 1, minus x squared, minus x cubed, and minus x to the 4th. And then when we simplify that, then that becomes this. So this is our expansion of 1 minus x to the 4th. Now, 1 plus 2a to the 6th will be the same sort of thing, except there'll be a whole lot more terms. So I'm not going to go through them, but you can see that pattern. The first term goes from power of 6 down to power of 0. The second term goes from power of 0 up to power of 6. And the coefficients in between, the 1, 6, 15, 20, 15, 6, and 1, are from Pascal's triangle. And again, we'll notice the symmetry. You might want to check that all of those numbers, 1 plus 6 plus 15 plus 20, etc., actually adds up to 2 to the 6th, which is 64. But I'll leave all that to you. And then, again, simplify it after that. And the very last one is just more horrible still, but it's still the same pattern. So when we do that, we just have now fractions to deal with. So it's an exercise in paying attention, not my strongest suit. So what's the big idea for this section here? Well, I guess getting an idea around how Pascal's triangle is built up, linking it to expansion of binomials, and knowing some of the properties of Pascal's triangle at this stage. So if you can carry that through to do these ones out of 5a, if you're finding that you are getting them really easily and they're exceedingly tedious, then of course be a little selective, but at least do enough to reinforce the patterns.